when running into electric field examples in the initial stages, you should be familiar and utilize symmetry as much as possible. So I'm going to just give you two examples where one example, it should jump out at you that the electric field at a point which is an equal distance from all of the charges in here on the circle is basically going to be zero. Okay, and then the other one will kind of change things up a little bit, and then we'll see, you know, that the amount of calculations is not always that hectic. Okay, so if you understand the problem. So here's the first example. So we have amount of charges, so they're uniformly spread around this circle. So the charge is simple, it's just 1 coulomb. And the radius of this circle has a radius of 1 meter. So the actual charges from the center are 1 meter away. So just that on its own is going to be, would have been just one single calculation if we wanted to find out what the electric field is at the center. However, if you take a closer look here and you start noticing that if you're starting to spread all of these charges, I mean, we could have had an infinite number of charges. So basically a uniform charge spread out on the whole kind of ring all the way around. And if they're the same distance away from the center as these are, you will notice that the actual electric fields will cancel each other off, now assuming that the charges are the same. So for instance, if you take a look at here, so let's say if you take this charge right here and then the opposite charge right here, now notice the charge is positive. So if you were trying to calculate and you took a look at the actual vector itself, you would notice that at the center right here, with respect to this charge, and because it's positive, so that means that your electric field will be pointing to the left. And then if you take this, then you have exactly the same thing, and this will be impacting that electric field, and this one would have been to the right. Now, because these two charges are identical, they actually cancel. So then there's nothing to do. So these two will cancel. Now, of course, so will these two, because one will have an electric field in this way, the other one will have it in the opposite way. So those ones will cancel. So therefore, this, and this is gone. And so will these, right? So the one from here and here, and because they're an equal distance spread apart, so that means this electric field is pointing this way, this one is that way, that's from these two, and they will cancel. And then the same thing will happen over here. So whenever you have symmetry, use it. So as much as possible to, allow yourself a much simpler problem. So this one, would be a nice problem to give students, especially on a quiz or on a test or an exam, just to see, all right, do you actually understand how these actual electric fields are with respect to some symmetry. So in total, this would have had 0 newtons per coulomb in terms of the electric field at this point, because everything would cancel. Now, if you take the same problem as you have in here and you start removing some of these, so here we have removed the bottom half, but we left the upper half and then the two on the right and the left, you might start thinking, well, okay, so these things won't really cancel each other off. So what is going to happen? Now, some of these will cancel, but some of them indeed do not cancel. So again, let's utilize symmetry, and then we're going to have to do the actual computation to try to find things out. But you'll notice that this isn't actually going to be that crazy difficult for us. So right away, whenever you do have symmetry, so when things are the same charges, but the same distance away, but on the opposite side. So that means this and this, the electric field from here. So as we said in the previous example, so these electric fields will cancel each other off. So there will be no calculations with respect to these. So really, the only ones that you will have, okay, some addition to, are going to be these three, because there is nothing on the opposite side of these that can cancel them off. So unfortunately, we do have something. So let's start with this one, for instance, and let's try to find out what that electric charge will be. Maybe I'll change this color. So we are working here at the center, right there, okay, and this one is going to have an electric charge. So I'm going to just draw this out rather big, okay, pointing downwards, and that would have been the electric field from here. All right, so that's the electric field from that particular point. Okay, so now if I want to be able to calculate this out, computation is very simple because of the fact that this is 1 coulomb and this is a radius of 1 meter. So if you substitute this back into your electric field equation, then you can see that the ones don't really do much for us. So therefore the electric field that we would have in this way is just going to be your K. So I'm going to just write K instead of writing the actual full numerical value, at least for the moment. So this is going to be K, and notice this is going to be Q, this is the R squared, so it doesn't really matter if it's squared because we're squaring radius of 1, so 1 squared is still 1. So really, that's what we have, except this would have been in Newton, okay, per coulomb, because the units would have canceled out. All right, so that's the value of K. When I'm writing K, I am referring to just the value, which is this right here. So that would have been, and pointing downwards. All right, so that would have been the first one. So maybe let me call this this as 1, okay, and let's put a 1 over here. Now, the other part, they're all the same. So from these two, they're going to be identical. So you're going to have exactly the same thing happening in here, except direction that we have is going to be in this direction. So let me shift this out of the way. So the number 2 over here will have exactly the same thing, except the direction is different. So it's still K, and this is N over C right there. Now, the one on the right-hand side, it's going to also have exactly the same thing, except it's going to be in this direction. Okay, so this is going to be all in the same angles right there. And it's the same magnitude for this. All right, so I have to kind of be careful in here. Let me try to draw this as equal distant as possible. So that is going to be 3, okay, and this is coming from this one over here. So they're all identical. Okay, so now that we have all of these, so what do? Well, we need the resultant electric field. So within here, the nice thing that's going to happen for us is that there are 2 components, right? So because we can create a triangle in here. So you're going to have a triangle over here like this. And then, of course, you're going to have the same triangle, okay, except over here. And now notice what happens, that the components in the x direction of those 2, so these 2, again, will cancel. So really, the only one that you need is the one in the y direction pointing downwards, right? So that's the one that we want to know, all right? So that's the one that we have. Now, because these are all equidistant, so within, so that angle, so if I stretch this out in this way, okay, and in this way, if we're talking about this angle, these angles are the same, and this is going to be 45 degrees within here because that charge is equidistant, okay, on that unit circle in this way. So 45 degrees, well, so that means, so this is 45 degrees, and obviously this is 45 degrees. So it's very easy to find out that component that we have. So if you take, it doesn't matter which one, so we know that the value in here, so this is the K, so 8.99 times 10 to the negative 9 newtons per coulomb. So that's the electric field within there. So that's that value. So now if I want to find the y component, so within here, so there we can just go ahead and use the sign. So this is going to be K multiplied by sine of 45, and we have it. And again, don't forget that this is just coming from the definition of sine. Okay, and this is the y component of, let's say this is a y component of 3, and it's going to be exactly the same thing. So 2 is going to have the exact same value. So, and sine of 45 degrees, which is 1 over square root of 2, or sometimes you might remember square root of 2 over 2. Now, once you have this, you can then find out the full electric field. This is going to be in the down direction, and that will be simply your electric field number 1, which is K plus. And now since we have 2 of these, so it's going to be 2 times K, I guess 1 over square root of 2. and we can do the computation as needed. So let me do that to finish this off. There you have it. All right, so that is it for this video. Happy studying. Bye everybody.